All right, looking at the enthalpy of the hydration lab. So using some data here, I'm going to make a note. Your numbers might be a little different. This amount of change in temperature is particularly large, but let's just work with it. We're starting out here with 11.056 grams of water, 1.797 grams of the sodium acetate. If I label this as 1 and this is 2, the mass of the solution is 1 plus 2. We're mixing these two together, and we're going to get a value for this set of data of 12.833 grams. And room temperature is your temperature initial, and this was measured to be 22.2 degrees Celsius. Final temperature was the maximum high or low temperature that you got. This temperature went up. This reaction is exothermic, and 32.2 degrees Celsius was the final. Delta T is always T final minus T initial, so that we keep track of our signs, and that's going to be 10.0 degrees Celsius. Now, what we're measuring here is we are measuring, so remember we took our bit of our powder of our sodium acetate, we added our water to this, and then we stirred it. This combination here is our solution. Remember, our solution is just a nice homogeneous mixture. And what happened is this solution got warm. And this solution got warm because when sodium acetate dissolved in water to make sodium and acetate ions, it released heat. And this heat came out here and went into our solution. Now, it is virtually impossible to measure the heat of an actual reaction. We can't isolate it, but it's easy to measure the heat of the surroundings, what it came into contact with, and that is our solution. So what we're going to do here is we're going to take our values that we have and calculate the heat that was gained by our solution. Our heat for our solution Q is going to equal the mass of the solution, call that 3. We're going to have multiplied the specific heat capacity, this guy right here, multiplied by the change in temperature. If we take and we put that through, we're going to get our value at 12.833 grams. Remember to add the water to the sodium acetate. Our specific heat, 4.18 joules per gram degree Celsius. That's going to be given. It depends on what substance you're using. Multiply the change in temperature, 10.0 degrees Celsius. When I multiply all of this through, I'm going to get a value here of 536 joules. Now, that is what was gained by this water sodium acetate mixture, our solution. But in order for our solution to have gained heat, our reaction has to have lost heat. And please note, because our Q value here is positive, that means our solution got warm. It gained heat. It gained heat because our reaction lost heat. How much heat did it lose? The exact opposite value, because energy or heat is conserved, and any bit of heat lost has to have been gained somewhere. So our Q for this reaction is going to be negative. You're going to find the opposite signs here, as you're going to find your delta T is going to be negative, which means your Q of your solution is going to be negative, and the corresponding Q of the reaction will be positive. That's for the second part. Now, what are we going to do with this? We are going to calculate a delta H. Delta H is how we normalize this so that it becomes an intensive, independent of the amount, rather than an extensive, depending on how much we have property. And we're going to do a delta H. Delta H is our enthalpy. It's our change in our heat. And we're going to define this of Q as the reaction in kilojoules divided by the moles that reacted. Be careful here that you use the right amount. My amount of sodium acetate here is going to be 1.797 grams. I'm going to need the molar mass of sodium acetate to get the number of moles for this. My molar mass is 82 grams per mole when I add those up. So I know there's 1 mole of my sodium acetate for every 82 grams. And when I do my math here, I'm going to get 0.0219 moles of this. My delta H is going to be the amount of heat. In my case, that was minus 536. Truly, your number will be smaller. This is pretty large. I need it in kilojoules. There's 1 kilojoule for every 1,000 joules. And I'm going to take and divide this by the number of moles. So I'm going to take down here, and I'm going to put my 0.0219 mole. And my delta H here is going to work out to be 24.4, 24.5 kilojoules per mole. Because this is a negative value, this is going to be a negative there as well, and we're going to keep track of this. We are going to do this for our delta H of the reaction of the sodium acetate trihydrate. Please note that this dot here means that the water is embedded. Remember, those were just crystals. They weren't like wet, dissolved in water. So when you take and you add this up, you're going to take your sodium acetate, which is your 82, and you're going to add 3 times the molar mass of the water to get the molar mass of the sodium acetate. And you're going to follow the same form. Now, after that, you are going to use Hess's law to figure this one out. So when we get to this part in the chapter, I'm going to walk you through this as well. Otherwise, this isn't going to make a lot of sense. And then if you go to the next chapter, this one is really straightforward. You really are just doing products minus reactants. You can figure this one out. And we're going to do one more Hess's law question here before we stop and the end this chapter. So go ahead and make sure you can do the first parts of these all the way through this. You should be able to read up on Hess's law and get a good start on what you need for this portion right here.